Hi, my name is Zach Buckholtz. Some of you may remember me as your TA for Physics 325. To those of you I haven't met, nice to meet you. Welcome. Today we're going to go through the setup for the Fourier Image Processing Lab for Physics 325. So it all starts down here with our helium neon laser that emits a wavelength of 632 nanometers. The beam then goes through this lens pinhole apparatus. Right? The lens focuses the beam down into the pinhole, and then the pinhole, after the pinhole, the beam will expand in a cone, producing a uniform wavefront, a large uniform wavefront, which is what we want for the Fourier image processing. Right? The beam then goes into this collimating lens. Right? So you can think of the pinhole as being the object, the light expanding out of the pinhole, and then the lens is at the focal length, one focal length away from the pinhole. The collimated beam then propagates down this optical rail to our slide holder. Before the slide holder, we have this iris to help clean up the beam pattern further. Right. So there's no sample in there now, but if there were, such as this wire mesh that we'll put in a minute, the beam would go through and then it would continue propagating. As you learned in lecture, after the beam goes through something like a wire mesh or grid, in the far field, the beam pattern will be the Fourier transform of the object that it went through. Right? However, to compactify things a little bit, we can have this lens, which will bring the Fourier transform from the far field to the near field, or the focal plane of this lens. Right? So what we want is the focal point of this lens to be at the top of this prism, so we can nice and easily see it with this piece of mylar. We can just set it right there and see what's going on top of that prism. Right? Then take the mylar out. The beam continues up, goes through this prism, bounces all the way down the optical rail to that mirror, and then all the way back here for a second far field. Right? So the light comes here, goes through the sample, goes through the lens brings the Fourier transform in the far field to the focal plane of the lens, and then our apparatus has that Fourier transform propagate into the far field again, and so up here we should see the Fourier transform of the Fourier transform. Right. So let's put in a wire mesh and see this in action. All right. So we have the wet mesh, comes in, goes through the lens. Let's put our piece of mylar in there. And on top of this prism, we see the Fourier transform of the wire mesh. Right? So then, if we let this propagate into the far field by having it go down and back, we should get the Fourier transform of the Fourier transform, which is just the image of the wire mesh. Hi, welcome. You've made it to checkpoint 1. Here we'll talk about what we qualitatively expect to see from the Fourier transforms. And so a Fourier transform is something that takes something in real space and shows what frequency components can be used to construct that structure, the real space structure. Right. So if we have a repeating structure in real space, we would expect to see something interesting in the Fourier transform. Right. So, for example, here we have vertical wires. Right? So as you can see in the vertical direction, there's not really much going on. It's pretty constant. So you can think of that as a wavelength of infinity. Right? So in other words, that's just a DC or zero frequency component. So in the Fourier transform, we would just expect to see one central dot in the vertical direction. However, in the horizontal direction, we have this repeating structure. Right? So that's going to give us some wavelength depending on how spaced the wires are. Right? And that's going to give us some more dots in our Fourier transform that represent a wavelength matching the spacing of those grid lines. Now, these grid lines are not a sine wave, they're points, or lines, very narrow lines, right? So instead of being just these two dots representing the sine wave, there will be some additional structure in the Fourier transform, and that will show up as additional dots on either side of the central dot. So now what do we expect if we have horizontal lines? Well, let's imagine we take these vertical lines and turn them horizontal, rotate them 90 degrees. We would expect the same thing to happen to the Fourier transform, right? Instead of having an infinite wavelength in the vertical direction, we have an infinite wavelength in the horizontal direction. And instead of having structure in the horizontal direction, we have structure in the vertical direction. Right? So we would take our Fourier transform for the vertical wires and rotate that as well. Right? So only one line in the horizontal direction representing just the DC component, and then all these components in the vertical direction representing the repetition of the wires. So now what would we expect from a wire mesh? Right? So in the previous two, we've learned that we can go from vertical to horizontal by just rotating the Fourier transform. Now the mesh looks something like the horizontal lines placed on top of the vertical lines. And since the Fourier transform is a linear operator, we would expect more or less a superposition of these two Fourier transforms on top of each other. The wire mesh is a superposition of horizontal lines on top of vertical lines. So the Fourier transform of the wire mesh should be the Fourier transform of the horizontal lines on top of the Fourier transform of the vertical lines. And we would expect something like a cross. So now what would we expect from a hole, a circular hole? Well, if we look in the vertical direction, we have something very uniform, and then a change where the hole is, and then at the top of the hole, another change, and then uniformity. And we have the same thing in the horizontal direction. We have blockage, 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 hole, 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 blockage, 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 blockage. And in fact, we have that in any direction as we rotate at any angle. So just like we got from the vertical wires to the horizontal wires by rotating 90 degrees, what would happen if we just rotated it a continuous angle all the way around? We would get something like a bullseye pattern. Like that.
And now, a quick word about spatial frequency.
Hello. We just got done discussing what would we qualitatively expect the Fourier transform to look like for each of these spatial filters. So now, what would happen if we changed the size of any of these filters, right? For example, what if we took these horizontal lines and spaced them out more? Well, we won't really expect any change in the horizontal direction because we still have long horizontal lines that go off to infinity and give us an infinite wavelength. However, by spacing out the wires, we are getting a larger wavelength in the vertical direction, right? So this central dot represents our DC component, or zero frequency, right? And the further away these dots are, and the further away from the DC component you get, the higher the frequency, and therefore the smaller the wavelength. So if we're spacing these wires out a lot more, the wavelength is getting larger, so these dots should get closer together. And same thing with any of these other patterns. If we space the vertical lines out further, the Fourier transform should get smaller.
Hi, David Gold here. Some of you might remember me from such days of the week as Thursdays. I'll be your guide for the next portion of the lab.
First, we insert horizontal wires into the imaging system. They're mounted in glass, which is very dirty and shows up in the image. The Fourier transform looks good though, and is a line of vertical dots just as we predicted. Now let's look at the wire grid again. This slide is also rather dirty, but as we predicted, the Fourier transform is a cross. Let's skip over the circular hole mask for now and look at checkpoints 3, 4, and 5 for the grid. First, we use a narrow slit to block everything but the horizontal dots in the Fourier transform. This now looks just like the transform of a row of vertical lines, and the image reflects that. Let's see that in action now by looking at the image as we quickly remove the mask. Wow. Next, we use an iris to block everything but the central bright dot of the Fourier transform. And here's the image. Once again, let's see that in action. Here, the iris is slowly closed, and you can see the clear image of the grid fade away as detail is lost. Now for checkpoint 5. We insert a small piece of glass over the central dot of the Fourier transform and rotate it back and forth. The image shows some interesting changes. With everything for the wire grid out of the way, let's go back and look at the Fourier pattern from a small circular hole. And now, here's Zach to show you a strange effect with that pattern described in checkpoint 6.
So, I'm using our translation stage to translate our sample, which in this case is just a pinhole. And as you can see, the Fourier transform does not move. However, the image, the Fourier transform of the Fourier transform, does move.
Thanks, Zach. Well, that covers the checkpoints in the lab, but while we're here, let's take a look at some other cool effects. Let's go back to that wire grid. I'm going to use the metal arm of the phase shifter to try to only block the central dot of the pattern. What do you think will happen? Wow, the image is almost perfectly inverted. To fully understand that, remember that it's the electric field of light that is being transformed, but that we see the intensity. Just for fun, let's watch the image as I slightly translate the metal arm to block and unblock the central spot. Amazing! Now, let's shift the phase of a component again, rather than completely blocking it. But this time, let's try it in one of the higher frequency components, rather than the central DC dot. The effect isn't as pronounced as with the DC dot, since much less of the brightness of the image is contained in this single high frequency component. But if you look closely, you can see horizontal lines moving off the grid as its phase is offset from the other frequency components. Okay, let's look at a slightly more interesting image next. We'll use this transparent ruler and put the 13 mark into the imaging system. Here's what we get. The magnification of the system is about 15, so it shows up very large on the screen. Scratches on the ruler are very apparent from years of arduous measuring. Here's the Fourier pattern. Images without very periodic structure tend to have transforms that look mostly like blobs like this, since a nearly continuous distribution of frequency components are needed to represent them. Now let's put an iris over it to serve as a low-pass filter like we did with the grid. The image then becomes very fuzzy. Remember, this is not a focusing or brightness issue. Blocking sections of the Fourier transform affect the entire image. You can think of this as a rudimentary image compression algorithm. By only keeping the lowest frequency components, we could store much less information to represent this image, but at the expense of detail. Now let's look at that in action. And here's that one more time, a bit faster. Let's see what Zach has to say about what's happening there.
As we just saw, as we close the iris and cut out the high frequency components of the Fourier transform, the image starts to get blurry. Why is that? Right, so here we have a very sharp transition in space. We go from 0 to 1. Right? So this happens over a very narrow region, and as we saw in checkpoint 1, things that happen over a very small spatial region will have a very large Fourier transform. And things that happen over a very large spatial region will have a very small Fourier transform. Okay. So this happens over a very small region of space. So it will have a very large Fourier transform. As we start cutting out the higher frequency components, it'll start blurring this sharp transition out and spreading out into a larger spatial region corresponding to a smaller Fourier transform.
Thanks again, Zach. Well, that's about all we have to show you. I'll leave you with one last strange effect. See if you can figure out what's happening. When we put a flame near the Fourier transform, look what happens to the image.